Today we're going to talk about special relativity. It's called special relativity because we ignore gravity. So we'll talk about what happens when we add gravity later. It's general relativity. But special relativity was developed by Albert Einstein in 1905 based upon the principle that the laws of physics are the same for all observers. You recognize from our previous lectures that the speed of light c is given by 1 over the square root of epsilon 0 mu 0. Epsilon 0 being the permittivity of free space, mu 0 being the permeability of free space. These are constants that can be measured about free space that is independent of an observer's motion. So therefore, the speed of light should be independent of an observer's motion. Now, this defies the common sense of what we've thought of before. If we think of someone standing and with a flashlight in his hand, and he's standing on a cart that is moving forward with a velocity v, and he shines the flashlight, shines the light at a velocity c, then the velocity should add, so the distance that the light travels in a certain amount of time delta t should be the distance that the cart travels, v delta t plus c delta t. At least that's what you would expect an observer on the ground to see. The observer sitting here on the ground watching, that's what he's going to see. But since he sees the light starting here and ending there, what he sees is the distance is equal to c prime delta t. So I can put primes on that. Now the normal tradition would be to say that d equals d prime. They both agree on the distance. Delta t equals delta t prime. They both agree on the time. So therefore, c prime would be the sum of the velocities v plus c. Unfortunately, this is wrong because it defies this c being constant. Well, if that's wrong, that means this is wrong and that's wrong. And so instead, what we get is c equals c prime, but d does not equal d prime, and delta t does not equal delta t prime. And so this leads us to two separate but related effects in special relativity. The first one is what we call time dilation. In time dilation, we have that times are different for different observers depending upon the speed you're going. And the reason why we call it time dilation is because the person who's measuring the time in the rest frame of the clock is going to measure the shortest time. Everybody else is going to measure a longer time. So we think of delta t, what is measured by everybody else, is going to be equal to delta tp, call it proper time, which is measured in the clock, times some dilation factor, gamma. We also have what's called length contraction. And that is different observers are going to measure different lengths. Now, the length of a ruler measured in the rest frame of the ruler is its proper length. But everybody else is going to measure a length that's different from that in LP divided by gamma. So that means that the proper length is the longest possible measurement of the ruler, and every other measurement is smaller. And this factor of gamma is given by 1 over the square root of 1 minus v squared over c squared. So it's a quantity that is always greater than 1. So for small velocities, velocity is very small compared to c, gamma is just equal to 1 and all the lengths are the same. And that is the case going back to standard physics. But as v gets larger and larger and approaches the speed of light, then gamma keeps getting larger and these changes occur much more. So I can give you just a simple example of how we measure this time dilation. If we think of a clock. And a clock is simply a beam of light bouncing from one mirror to another mirror and back again. And so you have a distance d, as you measure between the two clocks, or the two mirrors. And so then the amount of time it takes to bounce back and forth between these mirrors is just going to be equal to, so delta t is equal to the distance divided by the velocity, so that's 2d divided by the velocity c. And so this is in the rest frame of the clock, so this is my delta t sub p, my proper time. Now if I think about this clock moving, and it's moving to the right at a velocity v, then what happens to light is it doesn't go straight up, it goes at an angle, hits the mirror after the mirror has gone there, and then bounces back down and hits the mirror back there. So now we can see in the reference frame of an outside observer, we see that we have a distance d there, and this distance here is given by v delta t, and this distance here is, of course, going to be what we have, d squared plus v over 2 delta t squared, and the square root, that's that distance. But I'm measuring this over a time delta t, so this distance is also going to be equal to c delta t over 2. So 1/2 of delta t times the speed c. So I can set these two equal to each other, and so I get a c squared delta t squared over 4 is equal to d squared plus v squared over 4 delta t squared. Or I get my d squared is equal to c squared minus v squared over 4 delta t squared. Or now I can solve for my delta t. Delta t squared is 4d squared over c squared minus v squared. So delta t is equal to 2d over, and I can factor out a c times square root of 1 minus v squared over c squared. Divide out c squared square root. And so this becomes 2d over c times gamma. So delta t is equal to delta tp times gamma, which is our original equation. And so this shows you that the proper time is always going to be the shortest amount of time. Every other time is lengthened by this term. Now, if I think about an example, say, for instance, I am moving with a v equal to 0.90c, then gamma is 1 over square root 1 minus v squared over c squared, which is just 1 over square root of 1 minus 0.9 squared, or 0.81. So it's 1 over the square root of 0.19, which gives about 2.29. So that means that for every second that is in the rest frame of the clock, 2.29 seconds have passed for the outside observer. Now, the interesting thing is that this happens, remember, it doesn't matter who is moving. If I am moving to the right with respect to you at 0.9c, you will see my clock shortened. And so for every second that passes on my clock, you'll see 2.29 seconds pass on your clock. But my moving to the right at that speed is exactly the same thing as my being stationary and you moving to the left at that speed, which means when I look at your clock, I think that your clock is going too slow. And for every second on your clock, 2.29 seconds pass on my clock. That's what leads to the twin paradox, and I'll let you think about that while I erase this board. Okay, before I talk about why it is that I think your clock is slowed down and you think my clock is slowed down, and we are both correct, I want to talk about the second item up here, which is length contraction. So, for instance, if I start out at Earth, and there's a planet A that is exactly 1 light year away. Now, light travels about a foot in a nanosecond, so it travels about 1 billion feet in a second. So light travels a long distance in 1 year. But if we just talk about time in years and distance in light years, it becomes very simple because c just becomes 1. C is a distance of 1 light year per year of time. So c becomes 1 in light years per years. So if I'm on the spaceship and I'm traveling in the spaceship at 0.9 c, you can think of, okay, how long does it take for me to get from Earth to that planet? And I can do that calculation because the distance is 1 light year, the speed is 0.9 c. So my delta t is equal to the distance, 1 light year, over 0.9 c, which is 1.11 years. So I get from Earth to that planet in 1.11 years. But I have time dilation. So if I look at my delta T-P, my proper time, what I see in that clock, it's going to be equal to delta T divided by gamma, or 1.11 divided by 2.29. And that gives me about 0.48 years. So while I'm traveling from Earth to the other planet, only 0.48 years have passed for me. But you think that may be a problem because if I travel 1 light year in 0.48 years, aren't I traveling at twice the speed of light? Well, I'm not. And I'm not because of length contraction. So the length, the proper length of 1 light year is measured in the rest frame of Earth and the other planet. But if I'm traveling at 0.9 c, I measure that distance as a length contraction. So the measure that I measure, length, is equal to the proper length divided by gamma. That's 1 divided by 2.29. And that means it's only going to be about 0.44 light years of distance. So it's length contraction of the distance between the two simply because of the speed that I'm going. So the proper length, 1 light year, is measured in the rest frame of Earth and the other planet, what I'm going between. The length that I measure is the distance between them. Because I have time dilation, I will view that as if it was length contraction. So time dilation and length contraction are just two sides of the same coin. And we can actually see this as examples. We have muons, which are just subatomic particles that are created in the upper atmosphere when cosmic rays just hit the atoms of nitrogen. It creates the muons, and the muons have a lifetime of 2.2 microseconds. So, and then they travel at about 0.99 c. So if we think about that, they have a lifetime of 2.2 microseconds. They travel at 0.99 c. How far do they travel before they decay back into photons? And we can just do the calculation. So the delta T is 2.2 times 10 to the minus 6 seconds times 0.99 times 3 times 10 to the 8th meters per second. And that gives us a total length of about 660 meters. Not very far. Well, it turns out that we measure these muons. They are created in the upper atmosphere and travel downward. And so we can measure them at the Earth's surface, even though the Earth's surface is far more than 660 meters from where they originated. Well, the reason why is because we have gamma is going to be 1 over square root of 1 minus 0.99 squared, which is about equal to 7. And so that means instead of having a lifetime of 2.2 microseconds, this is the proper time, the actual lifetime we measure is 7 times 2.2, or 15.4 microseconds. And that means that the length, that's my delta t, so this is my length. My length is going to be equal to gamma times 660 meters. And so 7 times 660 is 4,620 meters. So it's 4 kilometers. And so that way we can actually see it. But we see it going this far. The muon in its lifetime only sees 2.2 microseconds. However, it's got a length contraction, so this is the length that it measures, the length I measure. But what it's going to do is say, okay, I only lived 2.2 microseconds, but I only traveled 660 meters because of the length contraction. Whereas I say, no, you traveled farther because of time dilation. So it really is just two sides of the same coin. So now we can get back to this issue of the twin paradox. As I am traveling from Earth to this other star, if you are on Earth, you will see my clock moving more slowly. But I, on my spaceship, see your clock moving more slowly. So we both think the other one has slower clocks. But if I turn around past the star and get back to Earth, the question is, which one of us is correct? Did your clock go much more slowly, or did my clock go much more slowly? Well, we can look at this by looking at what we call a space-time diagram. Now, a space-time diagram is simply where you put the time on the vertical axis, space on the horizontal axis, and think about motion. So light traveling at c equal 1 will travel in a straight line like this, and we think of everything in the future is inside that light cone of the future. Everything in the past is inside that light cone of the past. Everything outside is elsewhere. And with this light cone, we can see the equation x squared plus y squared plus z squared minus c squared t squared is equal to a constant. We may disagree on the x, y's, and z's, and we may disagree on the time, but when we add these together, we get constant. And as you can see, any path between a point in the past and here, or between here and a point in the future, is always going to be dominated by time, so this is going to have that length be negative. And we call that a time-like path. And for any time-like path, I can actually set of motion someone who is just moving along that path, so the time is moving forward at rest with respect to him. I can also draw some path between here and here, where it's what we call space-like. And so I can draw that, or I take some other point here. These are space-like paths where this quantity is positive. And for any space-like path, I can have a reference frame, like in this one, the one I have right here, or this one is the one that's moving with the velocity. That is a reference frame where that is simultaneous. So time equals 0 and only my delta x's. You notice then that any path along these lines of light is light-like, and that is going to be 0. So x squared minus c squared t squared is always equal to 0 for light. So that means the space-time distance for light is 0. So we can think about light leaving the sun. If you could travel on a beam of light from the sun to Earth, you know that about 8 minutes would pass by the time it got from the sun to the Earth. But if you were traveling at the speed of light, so you were traveling with that beam, actually the separation would be light-like and there would be no time passing. So the instant that you left the sun, you would perceive your arriving at the Earth. And so that's a light-like trajectory. Okay, with that, I go back to the twin. So I'm starting on Earth. I'm going to this planet at 0.9c. I turn around and head back to Earth. So let's draw the diagram. We have Earth here, and we have the planet A here. And so in their reference frame, this is the x-axis, and this is the t-axis, and then this would be the t-axis for the other planet. So I travel from Earth to the other planet. But in my reference frame, simultaneity has changed. So in my reference frame, my x prime axis is there. And then I am traveling on a trajectory that goes up like this. So according to this trajectory, from here to here, I have 1.11 years have passed. According to this distance here, this is 1.0 light years. But this distance here is only 0.44 light years. Now this may not seem geometrically obvious because this distance looks larger than this one. But if I take this quantity as my x squared, and this quantity as a minus c squared t squared, obviously the hypotenuse must be less than that. So it's because of this minus ct, anything I'm subtracting there means that this is going to be a smaller number. So according to this reference frame, there's a distance of 0.44 light years. Now what happens is that that's my x prime frame. Well, just parallel to that, as I'm approaching the star, this too is my x prime at that time. And so as you can see, what I consider as simultaneous points and what you consider as simultaneous points are different. And that really is a secret behind the twin paradox. So what happens is that this is 0.44 light years. I think that only 0.48 years have passed when I'm that. But when I look at you, I actually see this much time, which is 0.48 years have passed. So you think 1.11 years have passed. I think 0.48 years have passed. It's only because of the fact that our x-axis are different. You have an x-axis like that. I have an x-axis like this. So as long as I am continuing in an inertial reference frame and you're continuing in an inertial reference frame, there is no solution. We can't say which one is going slower, which one's going faster, because this stays consistent. But this is planet A here. I take a loop around planet A and I start heading back toward Earth. And I head back toward Earth at a trajectory like this. And I get up there, and sure enough, you think, okay, another 1.11 years have passed to that point. So on your clock, 2.22 years have passed. But as soon as I get around the other side, my x prime axis is going to be this way because I'm going the other direction now. And so what's going to happen is that while I'm traveling back, you think only 0.48 years have passed for me. I think only 0.48 years have passed for you, but the 0.48 years that I'm seeing of you is just this. So when I get back, I really am just under 1 year older and you are 2 years older. But the reason why is because of this missing gap. So this is the missing time that solves the twin paradox. So the bottom line is, as long as we both are going in an inertial reference frame, I think you're going slower, you think I'm going slower. But as soon as I change, I'm no longer in an inertial reference frame because I'm accelerating, then what's going to happen is as I accelerate, this simultaneous curve very quickly moves from there to there. So if I could actually see you as I was passing that planet, I would think that you would aging very, very quickly for that duration because of my acceleration. But while I'm in an inertial reference frame going to the planet, while I'm in an inertial reference frame coming from the planet, I still think your clock is going slower and you think my clock is going slower. So that's the solution to the twin paradox. Okay, things become a little more interesting when we add a third observer. Because in what we looked at so far, everything has either been measured in the reference frame at rest with respect to the Earth or at rest with respect to me. What happens if something is not at rest with respect to either party? If I've got a party that has a motion and you see a motion, but we see different motions, then we have to do the transformation between them. Okay, what I want to talk about now is called the Lorentz transformation. And the Lorentz transformation just tells you how to convert between your reference frame and my reference frame. So we have x prime and t prime given as a function of x and t. So x prime is gamma x minus vt, and t prime is gamma t minus v over c squared x. Now, because of the fact that if I'm moving to the right with a velocity v with respect to you, it's the exact same thing as you moving to the left with a velocity v with respect to me. So the inverse transformations, x and t, should just be the same thing, gamma x plus vt and gamma t plus v over c squared x. Now, it may not seem quite intuitive that if I just take and solve for x from that, I'm going to get this. But I can do that and show you that it actually does work. So if I take this equation and this equation, and I want to factor out the t, then I get x prime is equal to gamma x minus gamma vt. And so if I divide everything by gamma v, this means x prime over gamma v is equal to x over v minus t. I do the same thing with the next equation. T prime equals gamma t minus gamma v over c squared x. Divide both sides by gamma. T prime over gamma equals t minus v over c squared x. Okay, I've got a t there, minus t here and a t there. I can add the two equations together. I get x prime over gamma v plus t prime over gamma is equal to x over v minus v over c squared x. And so if I multiply everything by v, I get 1 over gamma x prime plus vt prime is equal to x minus v squared over c squared x. Well, you notice that this just is x times 1 minus v squared over c squared, which is just 1 over gamma squared. So this is x over gamma squared. So now I multiply both sides by gamma squared. I get x is equal to gamma times x prime plus v t prime. No, all of these have primes on them. And I have what I came in. And I can do the exact same thing to show that this solving these two equations for t gives me this. So this is the Lorentz transformation. So given these Lorentz transformations, we can look at any point, any value x and t that I measure can be an x prime and t prime that you measure, and we can understand what they are. And so I want to show that the space-time equation that we wrote, which is that x squared minus c squared t squared is equal to a constant. Okay, I want to show that x squared minus c squared t squared is a constant under the Lorentz transformation. So if I take x prime squared minus c squared t prime squared and see how that comes out in terms of x and t. So this is equal to x prime squared is gamma squared x minus vt squared minus c squared t squared times gamma squared t minus v over c squared x squared. So I multiply this out. This is gamma squared x squared minus 2 gamma squared x vt plus gamma squared v squared t squared minus c squared t squared gamma squared, c gamma squared, c squared gamma squared t squared, and then plus 2 c squared gamma squared v over c squared tx minus c squared gamma squared v squared over c to the fourth x squared. Okay, we can see right away that this term here, the central term, 2 gamma squared v tx and 2 gamma squared v tx cancel each other out. And so what I'm left with is a gamma squared times x squared there, and the c squares cancel out, makes that squared. So I get gamma squared x squared, and I just get a v squared over c squared. But this is just 1 over gamma squared, and that's gamma squared. That becomes x squared. So now I look at the next term, which is plus gamma squared v squared t squared minus c squared gamma squared t squared. So I get a v squared and a c squared. So this becomes plus gamma squared v squared minus c squared t squared. So this is plus gamma squared, factor out a c squared, becomes minus, becomes v squared over c squared minus 1 t squared. So this becomes x squared. This becomes plus. Now this quantity is just minus 1 over gamma squared. So this becomes minus c squared t squared. And we're done. And so, sure enough, I get the quantities are invariant under transformation. But if you look at these Lorentz transformations, you find that in this case, I think that your length is contracted. You think my length is contracted, but the times come in there differently. Okay, and so this gets you back the proper length and proper times appropriately. We will continue this in the next lecture, looking at velocity transformations, and then we will finish with a discussion of general relativity.